In drawing our covalent Lewis structures, we may have noticed that sometimes we can write more than one valid Lewis structure for a molecule. This occurs typically when we have double or triple bonds and we have more than one option for where to make that double or triple bond. Consider the example below, same molecule, drawn twice. At this point I've distributed all of the valence electrons, but we can see that the carbon in the middle is not satisfied yet, does not have its octet. So we have two choices. On the left-hand side, for instance, I could move the electrons from the top oxygen to form a double bond, and everyone would be satisfied with that octet. Or on the right option, I could use that other oxygen, force him to share his electrons, and I could form the double bond with the oxygen to the right. Both of these are valid. They'd be fine ways, but they are two different Lewis structures. So we call these resonance structures. Resonance structures are just two different structures or two different ways to draw a Lewis structure for a molecule. This always brings up the question, well, what does the molecule really look like? And it turns out the real molecule is what we call a resonance hybrid. It's kind of an average of all the possible resonance structures. So here we have two resonance structures. So you can consider when you have two people who have a kid, that kid usually looks like a mix of the two parents. So our real molecule, what we call the resonance hybrid, is going to look like a mix of these two resonance structures. Now, in this example, the two resonance structures are equivalent. Either way, the carbon is going to end up singly bonded to one hydrogen and one oxygen and double bonded to another oxygen. But sometimes you have resonance structures that are not equivalent. So, for instance, consider these two possible Lewis structures for CO2. I could either have CO2 with two double bonds, as shown on the left, or I could write CO2 with one single bond and one triple bond. And when you have two resonance structures that aren't equivalent, they have two different pictures at the end, one of these is usually preferred. When we say preferred, that just means it has lower energy. Molecules are always trying to lower their energy, so they're going to prefer the structure with the lowest energy. So the question, of course, becomes, how do I know? How do I know which one is preferred or which one is best? And we can use something called formal charge to decide. Formal charge is basically a fictitious charge that takes into account how many valence electrons the neutral atom has and how many valence electrons that atom sees once it's in the molecule. So we can calculate formal charge by this expression here. You just count up the valence electrons in the neutral atom, we get that from the periodic table, and subtract the valence electron in the bonded atom. And to get the valence electrons in the bonded atom, you look at it within the Lewis structure, you add up all of its lone pair electrons, and you give it half of its bonding electrons, and you assume the other half will go to the other atoms it's bonded to. Really, really easy way to do this is you do the valence electrons, you subtract the dots, which are the lone pairs, and you subtract the lines. Each line represents two electrons, but you give one to each atom. So valence electrons minus dots minus lines. Once you've calculated the formal charge, we can use our rules, which I'll talk about in a second, to figure out which resonance structure is best. So here's our two CO2s, or CO2 structures. So let's just go ahead and calculate that formal charge. Make my pen a little bit smaller. So let's start with this top one. The oxygen on the left, oxygen has 6 valence electrons. Here it has 4 dots, and it's connected to 2 lines, so his formal charge is 0. The carbon in the middle, carbon has 4 valence electrons. He has 0 dots attached to him, but he has 4 lines, so his formal charge is 0. And the oxygen on the right, oxygen again has 6. He has 4 dots connected to 2 lines. His formal charge is 0. Now for the molecule on bottom, the other way we could draw CO2, we'll start again with the oxygen on the left. Oxygen has 6. This guy has 6 dots and 1 line, so his charge is -1. Carbon here has 4, still 0 dots and 4 lines, so he is 0. And the oxygen on the right, oxygen has 6 valence electrons. Oops, that's a 6. And then 2 dots here and 3 lines, so this gives me +1. So once you calculate formal charge, we need to know how to kind of assess it and decide, first of all, did we do it correctly? And second of all, how do I know which one's better? So to determine if you did this correctly, you can look at rules 1 and 2. For a neutral molecule, which is what we have here, if you add up all your formal charges, they have to add up to 0. And we can see that's true in both cases. Here, a bunch of zeros, so of course they add up to 0. Here, if I add these together, the -1 plus a +1 also gives me 0. So that's a good way to check that you did all your formal charges correctly. If you had a polyatomic ion, let's say the nitrate ion has a charge of -1, then all your formal charges have to add up to the charge on that ion. So for nitrate, they would add up to -1. That's how you can check that you've done it correctly. To use your formal charges to pick the best structure, we can look at rules 3 and 4. Molecules or atoms prefer to have formal charges of 0. So the closer you can get to 0, the better. So in this case, we see we have a clear winner in the top molecule because all its formal charges are 0, whereas in the bottom, one of my oxygens has a -1 and one of them has a +1. So this is going to be my preferred resonance structure. Sometimes you can't make everything be 0. You're just left with some formal charges. So when we look at rule 4, if you have to have formal charges, the negative formal charges should go in the most electronegative atom. So you can look at the periodic table to determine which atom is most electronegative, and that guy should get the negative formal charge. So once again, we say, okay, so these are 2 possible resonance structures. What does the real molecule look like? It does, again, look like kind of an average of these 2 resonance structures, but this preferred structure up top, he is going to contribute more to the overall molecule. So that's like when you know 2 people who have a kid together and their kid looks a lot more like one parent than it does the other parent. So in this case, the real molecule is going to look a lot more like this guy, the preferred resonance structure, and only look a little bit like this second guy down here. So if you had 5 resonance structures, your real molecule would look like an average of all of these, but the lower energy or preferred resonance structures, the ones with these lower formal charges, they're going to contribute more to what the molecule looks like. So the real molecule is going to look more like those particular Lewis structures. So let's look at a couple examples of how to draw resonance structures and calculate formal charges with these 2 examples right here. Oops. This a little thicker again so we can see my dots. So we're going to write the Lewis structure that obeys the octet rule for each molecule or ion, and then we'll assign formal charges to each atom and decide, are these equivalent Lewis structures or is one better than the other? So let's start with O3 here. So first we'll calculate how many valence electrons we have. So we have 3 oxygens, each one has 6 valence electrons, so we have 18 valence electrons to work with. So I've got 3 oxygens. I've used up 4 of them. It gives me 14 left. 2, 4, 6, 8, 10, 12, 14. So now I've used up all my valence electrons. So I can see here, this oxygen in the center is not satisfied. I'm going to have to make a double bond, and that's how I can tell I'm about to have different resonance structures, because I could either pull my double bond from the left oxygen or the right oxygen. So let's just go ahead. Just going to draw the same picture again so we can see our 2 options. So on the one hand, I could pull from the oxygen on the left, and on the other hand, I could pull from the oxygen on the right. So these are my 2 resonance structures. And we can see right away that these are equivalent resonance structures because either way I have an oxygen in the center. He's single bonded to one oxygen and double bonded to another. So now I can calculate my formal charges, and I really only need to do it for one of them because it's going to be the same for the other one. So let's pick this bottom one down here. We'll look at the oxygen on the left. Oxygen has 6 valence. This guy has 6 dots, and he has 1 line, so he's going to be -1. This oxygen in the center, try and draw it up here, he's got 6 valence, 2 dots, that's a 2 there, and he's attached to 3 lines, so that gives his charge to be +1. This oxygen over here, he's got 6 valence electrons, 4 dots, and 2 lines, so his formal charge is 0. So I can see right away that I've done this correctly, because if I add up all the formal charges, they do add up to 0, which they should. And I can see that this guy on the left is going to have a -1 formal charge, the guy in the middle is going to have a +1, and the guy on the right is going to be 0. I can't make them all be 0 this time. There's just no way to do it. So this is just the best that I can do. And the structure on top is going to be the exact same. That single bonded oxygen is going to be -1. Guy in the middle is going to be +1. And the double bonded oxygen is going to be 0. All right, let's look at a second example. Now we'll look at, NCO minus here. This guy takes a little bit of space, so let's do him on the next page where I got a lot of space. So we're going to do NCO minus. So the first thing I want to do is add up my valence electrons. Nitrogen has 5, carbon has 4, oxygen has 6, and then I have a -1 charge, so I'll add in 1 more, so that gives me 16 valence electrons. So here I'm going to have NCO. Carbon goes in the middle because he's the least electronegative. That's always the guy who goes in the middle. I've used up 4, so I have 12 left. I'll go 2, 4, 6, 8, 10, 12. Once again, I can see that the center atom does not have an octet. I've used up all my valence electrons, so I'm going to have to start making double bonds. So now is when I know I'm going to have different resonance structures. So I can see that I have a few options. I could pull a double bond from each side, or I could pull a triple bond from one side and a single bond from the other. So I'm actually going to have 3 resonance structures this time. So I'm just going to start off the same spot for each of them. There we go. The top one, I can make both of them share. The next one, I could make the nitrogen share 2 pairs. And on the bottom one, I could make the oxygen share 2 pairs. So resonance structures are pretty easy to draw. Just once you realize you're going to make some double bonds or triple bonds, think about all the different ways you could make them. And then the last thing we want to do is pick the preferred structure by calculating formal charge. So I'm going to try and write it over to the right here. So on the top one, for my nitrogen, nitrogen has 5 valence electrons, and he's got 4 dots on him, and he's got 2 lines attached to him. So that nitrogen is going to be -1. Carbon has 4 valence electrons, 0 dots, and 4 lines, so he's going to be 0. And the oxygen here, oxygen has 6 valence electrons, and this guy has 4 dots and 2 lines, so he's going to be 0. So I can check I did it correctly. When I add up my formal charges, I get -1, and my NCO has an overall charge of -1, so that tells me I did it correctly. And I can see right away this is not going to be the best Lewis structure because the negative formal charge is on the nitrogen, but the oxygen is the most electronegative element. So I want to end up with a formal charge of -1 on the oxygen, not the nitrogen. So let's look at my other 2. Second one, nitrogen, again, 5 valence electrons. This one only has 2 dots and 3 lines, so that's 0. Carbon's pretty much always the same here. 4 valence, no dots, 4 lines, so 0. And then my oxygen here, 6 dots. This time I've got, 6 dots and 1 line, so he's going to be -1. Again, they all add up to overall -1, and if I had to guess, this is going to be my best Lewis structure because it puts the -1 charge on this oxygen, the most electronegative element. So I think that's going to be my winner, but let's check the last one, just see what we get. Here, my nitrogen, again 5. This time I have 6 dots, 1 line, so that's going to be -2. Carbon, like usual, 4, no dots, 4 lines, it's going to be 0. And my oxygen here, I have 6 valence, but here only 2 dots and 3 lines, so that's going to be, it's getting a little messy, let's rewrite that. 2 dots and 3 lines, so that's going to give me +1. Overall, they add up to -1, so that's good, but I know this guy really isn't going to be good because oxygen has a positive formal charge, and we definitely don't want that. He wants to have the most negative formal charge. So my preferred resonance structure is going to be this one in the middle, has the lowest overall formal charges, and it puts the negative charge on the most electronegative atom. So when I think about the real structure of the molecule, it'll look like an average of these three guys, but the one that will contribute the most will be this middle guy, because he's my preferred or lowest energy resonance structure.